Hello, my name is Chris Fallin, and I'll be talking today about an idea called deferred borrows. This is a way to make static memory management more flexible in languages like Rust that use ownership, borrowing, and lifetimes to reason about and ensure memory safety. In this talk, I'll give some background on Rust first for those who are not as familiar with the language. I'll motivate the problem based on language limitations that can lead to cumbersome code and a form of logical unsafety as well. I'll briefly describe static path-dependent types, which are the core primitive we add to the language. I'll finally describe deferred borrows, which are a container data type API design pattern built on static path-dependent types. Rust statically reasons about the memory that a program allocates and references that it holds to that memory. It handles memory allocation and deallocation in a very simple way. Every object is owned by one owner and is consumed when it is used by virtue of a linear type system. This means that, for now, we can see the heap as a tree of objects with no other pointer, crosslinks, or references other than the owning one. In this example code, we define a struct S that holds a heap allocated T. When we say lit T equal S.T, we move the pointer, and thus the ownership of the heap storage, out of S.T and into the local variable T. The type checker, or more precisely the borrow checker, will statically indicate an error if we try to use S.T later. Rust adds back the ability to have other pointers to things by introducing borrows. A borrow is a reference to an object that can be created or borrowed when one owns an object. It does not consume the object, but it temporarily takes ownership of it. In other words, borrows are integrated with the tracking of ownership transfer. Rust allows two types of borrow, immutable or mutable. When a mutable borrow exists, no other borrow can exist, and access to the original object is blocked. When an immutable borrow exists, access to the original object is read-only. The one-writer, multiple-reader property is the building block that gives Rust its safe parallelism and many other correctness properties. In this code snippet, we take a mutable borrow of the struct S. Because it is live up to the call to F, it is a type error to use the original S. Once control returns from F, the borrow is no longer live, and we can use S again. The ownership and borrowing system is a neat way of organizing storage at the language level, but to really be useful, we want it to be a building block for library APIs as well. Rust provides lifetime annotations that allow a library author to describe how borrowing interacts with their API. A container, such as a vector or array of objects, or a hash map, typically owns its contained elements, but allows the owner of the container to borrow elements in exchange for a borrow of the whole data structure. In other words, the smaller borrow of a single element is expanded, in an imprecise but sound way, to a borrow of the entire container. The library author annotates this by attaching the same lifetime to the self parameter on a method as its returned borrow, as shown here with the tick_a lifetime. So what are the potential issues with this language and library design? Let's look in more detail. In many languages, it is a common idiom to keep objects in one container, but also hold references or pointers to them elsewhere. There are several reasons one might want to do this. For example, some data structures inherently have crosslinks outside of an ownership tree. A graph is a canonical example. In other cases, one might keep references to objects indexed by some secondary key. For example, a hash map to quickly look up nodes in an array or graph according to some property. Algorithms also often keep references to objects as they traverse through data structures. These cursors are sometimes encapsulated in iterators and sometimes explicit. Either way, it is useful to keep bookmarks of a sort into the inner parts of a data structure. Expressing this idiom, that is, holding secondary references to container elements elsewhere, directly in Rust, is problematic at best and usually not practical at all. This is because Rust's borrow system does not distinguish the mere existence of a reference or borrow from its use. Once the borrow exists, it reserves the thing that it borrows. Hence, for example, one could not create two mutable references to container elements at the same time, even if they were different elements. Of course, for these reasons, holding direct pointers or borrows for long durations is usually not idiomatic rest. Instead, when flexible references into a data structure are needed, the common approach is to store the information needed to reach that element, or a sort of logical address. For example, if objects are in a vector, one might store array indices. Thus, the canonical Rust graph implementation shown here simply stores the adjacency list, what would be a list of node pointers in other languages, as a list of node indices instead. This works fine except for two problems. The first we highlight here. It is simply less ergonomic to have to index data structure nodes explicitly rather than to follow direct heap pointers. By paying this price, of course, we get all of Rust's correctness guarantees in return, from safe parallelism to freedom from iterator invalidation bugs, but it's certainly less than ideal. The second problem is that such an approach can actually be error-prone at a logical level. To see what we mean, consider what happens if we modify the list of graph nodes in some way, such as sorting them, or if we wish to remove a node in the middle of the list. The canonical answer is simply don't do that. Rather, like arena allocation, free all nodes at the end. One can allocate new nodes at the end of the vector, but that's it. Or, what happens if we use a node index with a different vector? This could be as simple as indexing the graph edges array with a node index instead. But we can solve that with better types. However, the type system can't always save us. Consider an algorithm that traverses two graphs in tandem, perhaps checking if the graphs are isomorphic. The programmer must take care to dereference each node index with the correct node array. This is another sort of memory safety. It's not literally memory safety as we usually know it, because Rust's type system still faithfully ensures that we never access deallocated or uninitialized memory, and never perform racy accesses. However, by using pseudo-pointers, we have brought back the moral equivalent of issues such as dangling pointers. In this work, we define logical memory safety as the property that every access to an object via a reference, for example, a pseudo-pointer or array index, accesses the same object that it was created to refer to. In other words, the reference is logically tied to a particular object rather than the path to reach it, and the object reached by that path must not change. So to summarize, in this work we observe that Rust programmers often avoid holding borrows to objects deep within data structures persistently because these borrows will conflict. Instead, they emulate pointers by capturing the path to access that object, such as the array index. However, the object reached by that path can change, or the programmer could access the path incorrectly. So we ask, can we encapsulate the path while tying it to the containers it traverses, so that the dereference is always logically memory safe? To do this, we'll introduce path-dependent types. A path-dependent type is a type that is subordinate to a particular access path or value in the program. Specifically, if we have objects P and Q of type T, and T has a type field U that is a path-dependent type, then P.U and Q.U are different types. A well-known example of path-dependent types exists in Scala. This language implements dynamic path-dependent types. This involves runtime overhead and dynamic checks. In this work, instead, we propose static path-dependent types. A static path-dependent type is annotated with a static access path. For example, the type T with field access path x.y.z. To make this work, we have to carefully define how unification works across different scopes, of course. I won't have time to discuss this now, but there are more details in the paper. In a bit more detail, for any type tau, written in a scope that has some access path, that is a local variable optionally with a string of field accesses, p, we can write tau/p. This type is a subtype of tau. This means that a value of type tau/p can always be cast to just type tau. That is, we can always strip off the associated path, but we can never forge it. The path can only be attached when the object is constructed. In this code snippet, given some struct we call vectorref, which we'll use to encapsulate array indices, we can write types vectorref/v1 and vectorref/v2 when v1 and v2 are local variables in scope. So now that we have static path-dependent types, we can finally talk about deferred borrows. We have everything necessary now to achieve logical memory safety. For the particular case of a vector, we can encapsulate its index in an opaque type and tie an instance of that type to the vector it refers to. We can let the user later provide both this opaque reference object and a true borrow of the original container to get a borrow of the element. Note a slight subtlety here. The container must guarantee that the object referenced at lookup time is still present at borrow time. In our example containers, we achieve this with a type system by allowing a one-way conversion to an append-only vector that disallows truncation. This brings up an important point to make. Logical memory safety is, in the end, a property of the container design. Path-dependent types are simply a building block to achieve this, and a deferred borrow is an idiom that uses path-dependent types to do so. So, to generalize and formally define it, finally, a deferred borrow is an object provided by a container that encapsulates a reference to an element. It comes from a lookup API, where we would otherwise expect to receive a true borrow in return. In turn, it provides a way to convert to a true borrow given the original container. The implementation guarantees that the object eventually borrowed is the same as at lookup time. I've used a vector as a simple example here, but we'll see a number of other data structure examples in a few slides. So let's look at a simple example. We start with a vector v, and we convert it to an append-only vector to allow us to take deferred borrows as described earlier. This code is going to iterate over the vector's elements and store references to the elements using deferred borrows. As we observe each element, here calling a function key to compute some secondary key, note that we need to pass a borrow to v, to key, as well as the deferred borrow itself. This is a small price we pay for the ability not to hold a true borrow. Instead, we need the container around so that we can obtain a true borrow when needed. To actually obtain a deferred borrow, we provide a simple method, deferred. This could be improved with some syntax sugar, of course. Finally, to use the deferred borrow, we invoke a method and give it a borrow of the container, in this case a mutable one, in order to get a true borrow. This true borrow exists only for the duration of the actual access. The two vector element references can otherwise coexist and be used for mutations to different elements at different times, unlike true borrows. Note that this is still memory safe because a true borrow of the container is needed to get a true borrow of the element. That is, we don't weaken REST guarantees, we just make the borrow checking more precise by narrowing the lifetime of the actual borrow. Let's look at how various container types can implement deferred borrows. We've discussed vectors so far and focused on a form of deferred borrow that ensures correctness by putting the vector in an append-only state. In order to implement deferred borrows for this container, the reference object only needs to hold the array index. And because the vector cannot be shrunk, the index will always exist. And when we convert to a true borrow, we know we can provide it. However, one could also implement a variant on a fully frozen vector that cannot shrink or grow. This would guarantee no reallocations, so the deferred borrow object could actually be a true pointer, which would be slightly more efficient. One could also provide deferred borrows on a vector that can grow or shrink, if one allows conversion to a true borrow to fail with an option of borrow return value. Similarly, for hash maps, there are several variants one could implement. In general, a deferred borrow is a concept that embodies a trade-off. Some work is done when the deferred borrow is created, and some is done when it is converted to a true borrow. How the split is chosen will affect what limitations are placed on the data structure in the meantime, what state is carried from the first to the second half of the operation, and how efficient the true borrow is. As a last refinement, we introduced the idea that a deferred borrow actually has all the information it needs to provide auto-dereferencing, like any other smart pointer implementation. This is because the path that is attached to its path-dependent type gives exactly the container object that is needed to convert to a true borrow. We propose defining a trait defBorrow that, analogously to the deref trait in Rust today, allows the compiler to deduce a way to obtain the necessary object reference, or borrow, when a deferred borrow object is used. Then, if we have code as in the snippet, and we use mute lm0 as an ordinary borrow, it can desugar to the shown def borrow mute call. That's it. That's all I have time for today. There are more details, of course, including a qualitative evaluation consisting of some case studies in the paper. As for current status, there is a prototype using tag types in current Rust, that is without the path-dependent type additions, that I will release. I also began to build support for true path-dependent types in Rust C, but this work is unfinished, and it's probably best if the idea is discussed further first. Thanks, and I hope you found this idea interesting. I'm happy to take questions here in the session or anytime by email.